Chapter 13 is revisiting the force of gravity. And now we're going to take a look at gravity in terms of some things that we didn't see before. We'll revisit the idea of Newton's universal law of gravitation, but we'll also introduce the concept of general relativity, which Einstein came up with in 1915. We're going to start, of course, with Newton's universal law of gravitation. And Newton's universal law of gravitation essentially says that anything with mass will pull on anything else with mass. And if we look at the history of this, we do know that Aristotle came up with this concept that there is natural motion, that things fall because they tend to go to their natural place in the universe. Of course, something made out of rock would naturally go toward the earth because the earth is made mostly of rock. Water would generally flow toward the ocean. Air would generally rise to its natural place, which of course is the atmosphere. But when we came across the Copernican revolution, when we got to the point where people began to question old ideas, a heliocentric model of the universe was soon accepted. And while Copernicus really didn't understand why the sun should be at the center of all motion of the solar system, he came up with a model which was then adopted by Kepler, or refined by Kepler, who found out some mathematical relationships. And we'll talk about Kepler's laws for planetary motion. This was really explaining the motion of the planets, much like we did with kinematics. We explained the motion of objects, but didn't explain the why. Robert Hooke was the first to really come up with an attempt to explain the why. He believed that there was an attractive force between the planets and the sun, and that perhaps this was associated with maybe something comparable to magnetism. But it was Newton who was able to unify what we already knew about gravity on the surface of the Earth with the gravity that holds orbiting bodies in their motion. Basically, the story was that Newton was sitting in his orchard one day during the plague years where he was away from university, and he compared the motion of a falling apple to the motion of the moon, which was up in the sky at the time, and its centripetal motion, or the centripetal acceleration that held the moon in an orbit around the Earth, and soon realized that the force that pulled the apple toward the center of the Earth was the same that pulled the moon toward the center of its motion around the Earth. And of course, later on, Einstein developed his theory of relativity, which explained some things that could not be explained with Newton's laws, especially under high accelerations. So again, here is Newton's universal law of gravitation, just looking at the magnitude of the force. The force on a second object due to a first object is equal to this gravitational constant, this universal gravitational constant. Big G, of course, is a little bit different from little g. Little g just works for the acceleration of gravity on the surface of the Earth, 9.8 meters per second squared. Big G works with anything with mass. With big G, it basically says that an object of mass m1, an object of mass m2, will exert an equal and opposite force on one another, F12, which is proportional to the product of their two masses divided by the distance that separates their centers of mass, r. So again, this is the magnitude of the force, and it's an inverse square law. And we see inverse square laws in many of the forces of nature. We see it in electric forces. To some extent, it does appear in magnetism also as an inverse square law. And that is important because these are the three fundamental forces in nature that we typically observe in the macroscopic world. In terms of its vector form, we can write Newton's universal law of gravitation as being equal to, for instance, the force on a second body due to a first body. Here we're taking a look at the force on mass 2 due to mass 1 we would say that, again, it's equal to this universal gravitation constant, big G, the product of the masses divided by the distance between the two masses, the percentage of masses squared. And then we introduce this unit vector, which points from the second mass center of mass to the first mass's center of mass. And that, of course, can also be written as the position vector of 1 with respect to 2 divided by the distance. So again, G is the constant of universal gravitation. We, of course, believe that this constant is universal throughout the universe. It is the same no matter what masses we're dealing with, no matter where we're looking in the universe. And again, this is an inverse square law, Newton's universal law of gravitation. And for the force of gravity, it's always an attractive force, meaning that we have no reason to believe that there's ever a situation where we have anti-gravity, where masses would repel one another. Even antimatter will have a positive mass and therefore will experience a positive force. This will have very important consequences, even though gravity is considered to be a very weak fundamental force. Because it's always attractive, it becomes an accumulative force. And therefore, when we pack a lot of matter into a very high density, we can get singularities where the force of gravity becomes so incredibly large that even light can't escape. We call this a black hole. Okay, so we want to derive an expression for the acceleration of gravity on a planet. If we think about the force between two objects, and we do a calculation between two masses, let's say, again, our universal gravitation constant 6.67 times 10 to the minus 11, think about this now. We look at these two masses. Let's say that they're, I don't know, they're about a centimeter apart. So that's 10 to the minus 2. 10 to the minus 2 squared is 10 to the minus 4. Let's say that the two masses are 1 kilogram each, just to keep everything fairly easy to calculate. And we have 10 to the minus 11 divided by 10 to the minus 4, roughly. We're doing an order of magnitude approximation here. And our force is still less than a micronewton between these two objects. In fact, you push them within a millimeter of one another, and that'd be very difficult to get the centers of masses of two 1 kilogram bodies even closer than that. You're still getting measurements which are in the micronewton range. So, normally when we're talking about the force of gravity, the force of gravity between two everyday objects is not going to be very significant. We have to go to a body which is massive enough where it can exert an appreciable force. And of course, this would be a planet, a moon, maybe an asteroid, which we're going to take a look at a little bit later. Even things like comets can have an appreciable enough gravitational force that it can be observed. But in any case, the force due to gravity, I'm going to rewrite this instead of as M1, M2. We're going to replace M1 with big M. We're going to replace M2 with little m. We're going to replace the distance between the two with big R representing the radius of the planet. So if I want to know the force of gravity due to a massive planet on a smaller mass m, where the planet has some radius big R, I would use this expression right here. But we also know that the weight of an object, say this little object, small m, by Newton's second law, is equal to its mass times the acceleration. In this case, we're looking at the acceleration of gravity. So if I want to know the acceleration of gravity for a planet, I can cancel out this small m with this m right here, and I get an expression for the gravitational acceleration on the surface of any planet, which is equal to big G times big M divided by big R squared, where roughly as the planet becomes more massive, the acceleration of gravity becomes larger and larger. As the radius of the planet becomes larger, the acceleration of gravity actually becomes smaller if we hold the mass constant. Now, here's the important thing. If we think about a sphere, and planets don't have constant density, but let's say we're going to assume a constant density here. If I grow the radius, okay, and the density is constant, the mass is going to go by the cube of the radius. So the mass is going to grow proportional to r cubed, whereas the acceleration goes down by r squared. So really, our acceleration for a planet of constant density, if we could change the mass, would grow linearly with the overall mass of the planet. So let's rewrite this, because for planets, we know we have terrestrial planets, which are made out of rock and metal, Mercury, Venus, Earth, and Mars. We have Jovian planets, which are made out of liquefied gases, primarily hydrogen, helium, methane to some extent. And these materials have very, very different densities. Again, the density of a planet does get greater toward the center due to differentiation. So we can't assume constant density, but if we think about, in the approximation where the density is held constant, we can, look at the surface gravity of the terrestrial planets and compare them to the Jovian planets and see that they're actually closer than you would think, given the fact that the Jovian planets are so much more massive. So let's rewrite this. We're going to take our expression for the acceleration of gravity on the surface of a planet in terms of mass and its radius. I'm going to say, okay, we're going to replace mass and volume with density, where volume for a sphere is 4/3 pi r cubed. Now, again, I have to warn you that this is assuming a constant density, and planets like the Earth have differentiated to have an iron core, where the outer layer is denser rock. But again, if I do this replacement right here, I can now solve for m in terms of density. The mass of a planet is 4 pi, again, assuming constant density, r cubed over 3. I guess that should be a large r right there. But again, substituting this into here, again, r would represent the radius of the planet. We can see that the acceleration of gravity for a planet goes by 4 pi g over 3. These are all constants, times the density times the radius. So two things here. The acceleration of the surface of a planet will be greater for a denser planet and will be greater for a planet of larger radius. So taking a look at our solar system, here's the Earth, okay? Here's our mass, here's our radius. We know that the acceleration of gravity is 9.8 meters per second squared. And of course, looking at all the different bodies in the solar system, assuming that we're calling the surface the top of the clouds, or the top of the denser part. For instance, the sun, here we're assuming that the acceleration is on the top of the photosphere. Of course, the sun extends far out beyond that as the corona goes off into space. But if you could stand on the photosphere of the sun, obviously it is very, very massive. Its density is roughly, can't remember its exact density. It's approaching that of water. But given that the sun is so many times more massive than our Earth, it's not surprising that it has a very, very large acceleration of gravity, 270 meters per second squared on the surface. Even if you could survive the intense heat, the intense radiation, you would be rendered unconscious instantly from the gravitational effects, because at 27 Gs, that would be more than you could circulate blood to your brain to stay conscious. You'd black out. Here's what's interesting. We compare Mercury with an acceleration of gravity of 3.7, about a third of the acceleration of the Earth's gravity, with that of Mars, and they're about the same thing. So you'd say, oh, okay, Mercury and Mars are about the same mass. That's not true at all. Okay. If I compare the mass of Mercury and Mars, Mars is about twice as massive. Why would Mercury have the same surface acceleration? And the explanation goes back to density. If we go back to this equation right here, the acceleration goes by the density times the radius. And although Mars is a much larger, more massive planet, Mercury is much denser, and its higher density allows it to have the same acceleration on the surface as Mars, which is about twice as massive. Looking at the other planets, again, we are going to talk about the surface gravity at the very top of the clouds. Jupiter is over 300 times more massive than the Earth, and its acceleration at the surface is 2.5 times greater than that of the Earth. So looking at Jupiter in this case, not surprising that you would experience 2.5 Gs at the top surface, because it is much more massive, but its density is also less than that of the Earth. But when we get to Saturn, Saturn's almost 100 times more massive. Even though it's 100 times more massive, okay, its density is significantly less than the Earth. So the two balance one another out. And if you could stand on the cloud tops of Saturn, there's no, solid surface there, you would experience about the same gravity as you would on Earth. In fact, Uranus and Neptune are significantly more massive than the Earth, but owing to their lower densities, you would experience about the same gravitational force on Uranus and Neptune. Of course, smaller bodies such as Pluto is not a planet, it's a dwarf planet. You would experience a very small amount of gravity, even less than what we experience on the moon. On the moon, it's about 1/6 the gravitational acceleration as it is on Earth. Pluto being very, very low in mass, even lower in mass than our own moon, you would experience a force of gravity that was less than 10% of what we have on Earth. Okay. Not only is the acceleration on the sun's photosphere, very, very large, when the sun sheds its outer atmosphere, it's going to lose a lot of mass, but most of it's going to collapse to become a white dwarf. And even though the mass would be comparable to the original sun, you would experience an increase in the acceleration of gravity of about 10,000 times, because you are taking a body which is currently 100 times greater than the radius of the Earth and shrinking it down to the size of the Earth. So by concentrating the volume, by 1,000,000 times, you get a much, much larger acceleration of gravity. Even more compact than a white dwarf is, of course, a neutron star. A neutron star is essentially something that's more massive than our sun, but no larger than the size of Manhattan. So, very, very high density. Essentially, this is nuclear matter, meaning that the atoms are no longer there. The atoms have been crushed into neutrons and essentially very, very heavy nuclei. And if we could crush a neutron star to an even smaller body, we would get a black hole. And with a black hole, our gravity is going to be essentially large enough to even trap light. Light can't escape from it. So again, going back to this equation right here, the acceleration of gravity on these different bodies in the solar system depend on how much mass is there and how concentrated the mass is. Obviously, the smaller the radius, the more we concentrate the mass. So we can either say the acceleration of gravity is proportional to the mass and inversely proportional to the radius of the planet squared, or the acceleration of gravity is proportional to the density of the body and the radius of the body. Okay, so later on, and this is really for the future, we are going to look at something called Gauss's law. This is typically covered in E&M initially, but any of your inverse square law forces, gravity is a conservative force, the electric force is a conservative force, they will follow what is known as Gauss's law. And essentially what it says with Gauss's law is that the strength of the gravitational field, and the best way to measure the strength of the gravitational field is really to measure the acceleration of gravity, but the strength of the gravitational field at any point in space is going to be equal to, and we're going to use a spherical volume right here, the mass of the mass of the body enclosed by this particular sphere. So again, it's a little bit difficult to explain Gauss's law in too much detail here. Typically with a Physics 1 course, you haven't taken Calculus 3, but you will come across this idea of divergence and Gauss's law that basically when we look at the acceleration of gravity can be calculated by enclosing some mass in a symmetrical surface area, usually a sphere, and calculating the acceleration of gravity, where the gravity really times the area of our surface is going to be equal to 4 pi times g times m. But again, this is something that you should keep in the back of your head for the future, because we really do cover that in much more detail when we get to electricity magnetism, specifically with electric force. Okay, here's a problem. When we look at Newton's universal law of gravitation, we see, of course, that F is equal to g m1 times m2 divided by r squared. So the question becomes, how do we measure the gravitational constant if on the surface of the Earth we may know the radius, okay? We may know the mass of what we're measuring, but g and the mass of the Earth are an unknown. You can't put the Earth on a bathroom scale and measure its weight. First of all, it's impractical, to say the least. Second of all, what are you comparing it to? Okay, you'd have to put it in some gravitational field to get a weight from it, and that just doesn't work. So how do we come up with the gravitational constant if every time that we're measuring gravity, we're measuring it using the Earth's gravitational field? Coming up with G was a very challenging experiment, and this was done by Henry Cavendish in 1798. So while we all knew how gravity behaved, that it was an inverse square law, this value for G eluded us for quite some time. And he came up with an ingenious way of measuring this. The way that he did this is he used this torsional pendulum. Basically, you have these two masses, which are sort of on a dumbbell type configuration. And this was suspended by a string, And the string, if you rotated these masses, would put some torsional force on the string or this fiber. And because of the elasticity, the torsional elasticity of the fiber, it always would want to go back to equilibrium. So essentially, we hang this dumbbell and allow it to just reach equilibrium. And then we bring these other masses up to it, and we see how much these two masses deflect. Now, again, we talked about the difficulty of measuring this earlier on because we're talking about forces in terms of, maybe micronewtons, even if we're getting these masses within one another, within, about a centimeter. So we need a very, very sensitive way to measure this. And because this fiber was very, very thin and the torsional elasticity was very, very low, and of course, all the other forces had to be canceled out. It had to be done in a room where there were no, air currents that could move the different masses. To magnify the motion of this dumbbell right here, Cavendish actually affixed a mirror on this and collimated a light source and shown this on a wall to amplify the motion. And he was successful in actually calculating this. So very, very elegant experiment, very ingenious experiment to come up with a value that was hard to obtain. And again, you can't use the Earth. The Earth is, very, very massive. It generates a very large force. But how does one calculate the mass of the Earth? You can assume that it's completely made out of the same rock that you have on the crust, but you come up with a very, very inaccurate value because, of course, we know the core is made out of dense iron. Okay, let's use this equation and just take a look at
unknown caller.
Some different values that we have as a function of altitude. What we're going to do is we're going to say the mass of the Earth, of course, is, now that we have the value for G, we know that it's 5.97 times 10 to the 24 kilograms. We know the radius of the Earth, where we are on the surface, is 6.37 times 10 to the 6 meters. And of course, G is our value for the universal constant going back, 6.67 times 10 to the minus 11 meters cubed over kilograms seconds squared. So looking at the surface of the Earth, we know that the acceleration of gravity is 9.81. That's at sea level. If we go up 1 kilometer in altitude, there's really not very noticeable of a change. Here, what we're doing is we're adding 1,000 meters to this radius right here, the radius of the Earth, and plugging it down in this equation here. Even if you climb a very tall mountain, and mountains are, I think the tallest mountain would be probably Mount Everest at about 40, a little over 4,000 kilometers tall. You can see the acceleration of gravity is still not noticeably different. It's still, less than 1% difference at that altitude. Okay. Going up into low Earth orbit, I think, 20 kilometers is probably getting low Earth orbit. Come on. What is the low Earth orbit? You're still going to be able to think, we'll say low Earth orbit, to about 2,000 kilometers. Still, the acceleration of gravity is not all that large. It's not until you get out to the distance of the moon that we see an appreciable change in the acceleration of gravity. And this brings up a very important point. If I'm in orbit, let's say I'm in orbit at an altitude of 2,000 kilometers, okay, why am I weightless up there? Well, it's the same reason why you feel weightless when you're in a roller coaster and you're falling downward. If you're actually in the process of accelerating downward, okay, you feel weightless. If you're in an orbit, you're actually falling around the Earth, okay? You feel weightless because you're actually falling, okay? It's only when you're on the surface and you're stationary that you will actually experience this acceleration, okay? Or you'll notice this acceleration because the normal force is pushing up on you. Okay, let's do another application. Ceres is a small dwarf planet. Okay, Ceres is, if you don't know, the largest body in the asteroid belt. It was at one time considered to be an asteroid. We've sort of upgraded it to a dwarf planet, much like Pluto is a dwarf planet. So it's the largest of the asteroids. And one time it was thought to be a full planet, but it's downgraded to an asteroid. Now it's upgraded to a dwarf planet. And again, please understand that these are just classifications that we impose on these bodies. These bodies don't really care what we call them. But let's say an astronaut drops a rock from a height of 10 meters, and it takes 8.06 seconds to hit the surface. Calculate the acceleration of gravity on the surface of Ceres. Okay? Then we're going to find the mass of Ceres, given that it has a radius of 510 kilometers, and calculate the acceleration of gravity 50 kilometers from the surface. Okay. First of all, astronaut drops a rock from a height of 10 meters. It takes 8.06 seconds to hit the surface. Okay. Pretty long time. Certainly longer than it would take to reach the surface of our planet. Remember, we can measure the acceleration using the kinematic equations. Of course, V naught T is going to be 0 here because we're starting at rest. So the distance that something falls is equal to 1/2 the acceleration times time squared. So now we say the acceleration is 2 times the distance divided by time squared. And we get 0.308 meters per second squared for the acceleration. So that's the surface gravity of Ceres by simply dropping a body, like we could do the same on the surface of the Earth. Now, how do we find the mass of Ceres for this at a radius of 510 kilometers? Okay. Okay. Once again, here's Newton's universal law of gravitation. Fg is equal to G m1 m2 over r squared. Of course, we'll take out the falling body out of this. So the object that we dropped times its acceleration is equal to this. So m2 is butt out from both sides of the equation. We get our surface gravity equation once again. Plug in all our numbers, solve for mass here. And we get that Ceres is 1.2 times 10 to the 21 kilograms, significantly less than the Earth. The Earth is, going back to when we looked at these different bodies, about 6 times 10 to the 24. So Ceres is 1.2 times 10 to the 21, more than 3 orders of magnitude less massive. Okay. Once again, we're going to now move from the surface and we're going to calculate the acceleration of gravity instead of at 510 kilometers, which represents the surface. We're going to go another 50 kilometers away. And, if we add, once again, this additional distance, we have 560 kilometers. We would get an acceleration. I did actually make a little error here. I didn't put the full distance, but again, we get an acceleration of 0.255 meters per second squared. So there are 2 errors right here. This is 5.6, and I actually did the calculation with 5.6. And that's an acceleration of gravity of 0.255 meters per second squared. Okay, sorry for that little error.